The inverse of a function is a new function that undoes the operations of the original. So for example, if we had a function f of x, if we plugged 2 into this function and we got an output of 5, well then in the inverse function, and the notation for that is like this with f to the -1 of x, that's the symbol for inverse. So if in the original function an input of 2 yields an output of 5, in an inverse function an input of 5 yields an input of 2. Or in other words, it just cancels out or undoes the operation of the original. And so another way of seeing it is if we had an ordered pair generated by the original function, 2 is the x-coordinate, 5 is the y-coordinate, then the inverse function would generate the point 5, 2, meaning when 5 is the x-coordinate, 2 would be the y-coordinate. And so we take advantage of this idea when it comes to trying to find the inverse of a function, like the one that we have here. And so what we're going to do is we're going to flip-flop the x and y in the equation, and then we're going to isolate y. We're going to solve for y, and then once we isolate y, the new equation, the new function that we have, will be the inverse of the original. And so the first thing we have to understand is that when we see f of x in an equation like this, we're just using function notation to represent y. So I'm going to first write it as y equals x plus 6 over 2. And so now I'm going to interchange x and y, meaning I'm just going to flip-flop the x's and y's. Anywhere where I see a y, I'm going to replace it with an x, and any place I see a x, I'm going to replace it with a y. So it's the exact same function, everything else stays the same, I just now flip-flop the x and y. And so now my job is to solve for y, and then the resulting equation will be my inverse. So I'm going to start off and multiply by 2 on both sides to get rid of this 2 that's in the denominator. So now we've got 2x equals y plus 6. And so then my last step to get y by itself is to subtract 6 from both sides. So if we scroll down a little bit to leave us a little bit more room, we get y equals 2x minus 6. Or if we want to stay true to our inverse function notation, instead of putting y there, we're going to put f and then the -1 exponent of x, indicating that it's the inverse of the original function f of x in this problem, equals 2x minus 6. So there's the way we want to write that inverse. And we can double check to make sure that we indeed have the correct equation by plugging in a number in for x, seeing what output it generates in the original function, then taking that output and seeing if we get back to that original input when we use it in the inverse. So let's say we plugged in 2 into this function. So I've got 2 plus 6 is going to give me 8. 8 divided by 2 is going to be 4. So that means I get 4 out after having plugged 2 in. So that means when I plug 4 into my inverse, I should get 2 as an output. And indeed, if we do that, if I plug in 4 right there, 2 times 4 gives us 8. 8 minus 6 gives us 2. And so we indeed end up with the opposite ordered pair. And if we tried this with other values, we would get the exact same thing. So the idea here is we're flip-flopping the x and y in our equation, remembering that f of x is really just a fancy way of indicating the y value, and so then we solve for y to get that inverse function. In the next example, we're going to do the same thing. I'm going to again remember that g of x is really just y. So now I'm going to flip-flop the x's and y's. So I'm going to have x equals the cube root of 1/3 y plus 3. So I need to get rid of that cube root as I try to solve for y. So I'm going to raise both sides to the 3rd power. So that will undo the cube root. So now I've got x cubed equals 1/3 y plus 3. So now I'm going to go ahead and subtract 3 from both sides. So I get x cubed minus 3 equals 1/3 y. And so now my last step to solve for y is to multiply both sides by 3. I just have to be careful that I multiply everything by 3, so I end up with y or like I said, we want to change that to the inverse of g of x. So I'm going to use g to the negative 1 of x this time, since my original was g of x, equals 3x cubed minus 9. And so if I'm inclined to do so, I can double check to make sure that I indeed have the correct inverse by testing a point. So for example, if we plug in, let's say we did 0, and we could plug into the inverse and then see if we get the opposite coordinates, the inverted coordinates, back in the original. So if I plug in 0 into my into my inverse function, I get 3 times 0, which is 0, and then 0 minus 9 is negative 9. So I got an ordered pair of 0, negative 9. So now I can go back to the original function, and if I plug in negative 9, I should get 0 as an output. So if I plug in negative 9 right here, 1/3 of negative 9 is going to be negative 3. Negative 3 plus 3 is going to be 0, and the cube root of 0 is just 0. So I'm indeed ending up with the opposite ordered pair with the x and y flip-flopped. So that confirms for me that I do indeed have the correct inverse function. Now, if we're given a table of values for two different functions, we can determine if those functions are inverses of each other if the only difference between the two tables is the x and y columns are flip-flopped. So I take a look at this first function here, f of x, and so it's generating these ordered pairs 2, negative 3, 5, negative 4, 8, negative 5, and so on. And so if g of x is going to be the inverse of that function, then just basically the top row and the bottom row are going to flip-flop. Nothing else is going to change. I'm going to have the exact same numbers, same positive negative signs. It's just my x coordinates are going to become my y coordinates are going to become my x coordinates. So in this case here, if we look, we can see in this g of x row, we should have 2, 5, 8, 11, and 14. Same as what we have in the top row as the inputs into the original function, but we don't. The negative signs have stayed here in the outputs, and the inputs are all still positive. But that should not be the case. We should just be flip-flopping these two rows. So it should be 2, 5, 8, 11, 14 for g of x, and then negative 3, negative 4, negative 5, negative 6, negative 7 for x. So in this case, these are not inverses. In the second example, we see that we do in fact have that exact flip-flop. So here we've got 0, 3, 6, 9, and 12 for the inputs, and that's exactly what we see here for the outputs, 0, 3, 6, 9, and 12. No change. And those are still paired with the exact same set of numbers as we had in the original. So the outputs in the original were negative 10, negative 8, negative 6, negative 4, negative 2, and here indeed we have the exact same set of numbers. So in each case, it's just the flip-flop of the ordered pairs. 0, negative 10 became negative 10, 0, and so on. So this one, we do have a couple of inverse functions.